Hello, this video is a direct continuation from the previous video, which was Worms Part 1. So if you've not watched that video, go and watch it now. You can click the little link above. At the end of the last video, we had a game where we could generate a random terrain and we could deploy units on it by clicking the middle mouse button, we could cause arbitrary explosions anywhere on the screen, and we could drop bombs on the scene, and the units interacted with the explosions. And admittedly, that was quite a long video because we had all of the physics stuff to get through. I'll try and keep this one a bit shorter. In this video, we're going to look at adding some user input so we can control the units and make them walk around the map. We're also going to add a smart camera, which will follow the action so the player can see what's going on. And finally, we'll introduce a state machine, which is used to coordinate and sequence all of the events that go on, i.e. we'll turn this from being just a playable demo into an actual game. Let's get started. I'm starting off with the code that's available on the GitHub, and it is the code that we created in the first video, so I'm going to change that 1 to a 2. At any given time, the player can control one of multiple units on the screen. So we're going to need to store a pointer for the object that's under control. And this pointer will be used to direct all of the user input towards that particular object. For now, I'm going to hack in that pointer points to the last worm, or the last unit, that was added to the map. So I'm going to borrow this code from here, create a new worm object, and push that to the back of the list. And this means I've got access to the pointer for my object under control variable. We won't be leaving it this way, but this allows us to do tests quite quickly. If the object under control pointer isn't a null pointer, then it must be pointing to something, and hopefully that's going to be a unit. In fact, what we're going to ensure through the rest of the game code is that p object under control always points to a worm unit, so it won't point to a missile or some debris. And then we should ensure that user input only applies when the object is stable. For example, we don't want the object to be able to jump whilst it's in mid-air, or it's falling. I'm going to use the Z and X keys to make the worm jump in a particular direction, Z for left and X for right. And to make the unit jump, we just need to set the velocity vector directly. So here I'm setting it with a positive X component so it jumps towards the right. And for Z, I'm going to set that to a negative X component. Because it's jumping, we'll have to set the Y component to be negative so it's working against gravity. Let's take a look. So I've created my Perlin-Noise map and I'm going to add a unit to it. Now the last unit added is the object under control, so right now all of my user input is going to refer to this one unit. If I press the X button, it jumps to the right. If I press the Z button, it jumps to the left. And I can't jump in mid-air. Clearly this object is jumping around on the moon, but that's nothing a little fine-tuning can't sort out later. The unit is only going to move via jumping. And the reason I've decided to do this is it's actually quite complicated to make it walk across the surface using the physics engine that we've got. But I'm going to disguise the inadequacy of the physics engine by making the player jump, because the player then has to take some risk. They have to estimate where their unit will end up. And if I add another unit, this is now the unit under control. Now Worms is a game all about angles. We use them to work out the trajectory to fire weapons, and I'm also going to use the angle to work out a jumping trajectory. So the user has some control over the jump, because right now, just by jumping backwards and forwards, I don't get very many options of where the worm can be on the terrain. The only variability comes from when the worm falls down hills. So let's add a trajectory cursor. This is where we're going to start adding some properties to the worm class. And in this instance, I want to add a shooting angle, which is a floating point. I'm going to add some more clauses now to the user input. So when the user presses the A key, I want the cursor to rotate counterclockwise. Now again, assuming that the object under control is a worm, I'm going to cast the object control pointer to a type of C worm, as this then allows me to access the shooting angle variable. So whilst the A key is held down, I'm going to be subtracting from the shooting angle with reference to F elapsed time just to make it smooth. But I'm also going to add in some protection that if we go below -pi, it wraps back around to +pi. This way the cursor can be aimed at any angle around the unit. I'm going to do exactly the same for the S key, except this time I'm going to be increasing the shooting angle. Naturally, we're going to want to visualize the cursor to the player, or else this game will be very tricky indeed. And currently we're drawing all of the units by automatically scrolling through the list of objects and getting it to call their own draw routines. But we want to add extra information, so we'll have to expand this loop a little bit. We still want the object to draw itself, but I'm also going to, again, cast the object under control pointer to a type of worm. And if the current object in the list that's being scrolled through is equal to that worm, then we know we're drawing a cursor only around the worm that is the object under control. Let's work out where the center point of our crosshair is. Create a variable cx, and we know it's going to be somewhere near the position of the object. And I'm going to use our old friends sine and cosine to turn our shooting angle into a vector. I'm setting the length of this vector to 8, i.e. the radius of the circle that is scribed by the cursor. There is one more thing to do. Of course, we're working in world space at the moment. We need to turn that into screen space. So I'm going to offset it by the camera position. I can do exactly the same for y. I just need to change my cosine into a sine. I then want to draw a black pixel at that location to represent the cursor, but I'm also going to draw the pixels to the north, south, east and west of the center pixel to make it look like a plus symbol. Let's take a look. So if I add a unit, we can see that there's a cursor attached to it. And I can use the A and S keys to rotate the cursor around the unit. And if I add another unit, which becomes the object under control, the cursor has moved from the unit we're no longer in control of. Let's use some similar code now to make it so that the worm jumps in the direction the cursor is pointing. So now I no longer want to hard code these values in. Instead, what I want to do is get the shooting angle for the object under control, which will be for that worm that we're now controlling, and use that angle to create a vector, in much the same way we just created the cursor. However, now I no longer need a jump in the other direction. Everything is governed by the cursor, so when the user presses the Z key, hopefully the unit will move in that direction. Let's take a look. Put the unit on, and if I jump, it's sort of nudging sideways. So let's move the cursor vertically and jump. There we go. We can see the worm jumps vertically. And now the user has a lot more control over their jumps. And when we put a time limit later on how much time the user has to play, it becomes a little bit more of a pressure, because it takes time to move this cursor. Currently the camera is completely controlled by the player and where they've got their mouse on the screen. I think it's more natural to have the camera follow the object that's under control, or indeed any other object that we want it to follow, for example a missile later on. So I'm going to create another pointer which points to the object that we want the camera to center on. This piece of code from the first video makes sure that the camera is always within a sensible space within the world map, so we don't go out of bounds. So it's important that we do all camera manipulation before we clamp it. And we only want to move the camera automatically if the tracking object is not null pointer. And in this situation, I want to set the camera's x coordinate to be equal to the object we're tracking's x coordinate offset by half of the screen. So the object is always in the middle of the screen. And I want to do exactly the same for y. In much the same way we hacked the object under control variable, I'm going to hack the camera variable too. Just for now. Let's take a look. So I put my unit on the screen and we can see the camera has already started to follow it. Let me move the cursor up a little bit and cause him to jump. And we can see the camera now follows the unit, keeps the unit in the center of the screen. In fact, we blow the unit up, it always stays in the center. But our clamping code should ensure that when we get towards the map boundaries, the unit moves from the center and we don't have a horrible crash. Now let's make it so the user can fire a missile. In the original Worms game, the user would hold down a button to build up an energy bar to indicate how much force they want to put into the projectile. So we'll do the same. I'm going to create a flag which is B energizing to indicate that the user is indeed charging something up, and I'm going to create a floating point which stores the amount that has been charged so far, and we'll initialize that to 0. And back in the section where we're handling user input, I'm going to make it so that the spacebar starts charging up the weapon. So as soon as the spacebar is pressed, we're going to set the energizing flag to true, and we'll reset the energy level. And one of the nice things about the console game engine is we can distinguish between the button being pressed and the button being held down. So whilst the spacebar is continuing to be held down, I want to increase the energy level. And of course I'm using f-elapsed time to make sure that all smooths out. And if the energy level goes to larger than 1, I'm going to clamp it, and then I'm going to do something else because it's at this point the weapon needs to fire. And it's important that we do fire here because it's this little pressure which punishes the player for hesitating about their shot, i.e. we're trying to introduce some skill that the player has to acquire in order to be good at the game. So I'm going to add an additional boolean which acts as a trigger to handle the firing of the weapon. We'll default it to false. And we'll make sure that we set it to false when the user starts pressing, so we don't want the weapon to fire straight away. We're going to set it to true when the energy level is at its maximum, so it fires the weapon straight away. But we also need to consider the case where the player is playing accurately and doesn't want to put the full force behind the projectile. And this will happen when they release the spacebar earlier, so we also want to look for this event. And in this case, as long as the weapon is being energized, as soon as the spacebar is released, the fire weapon flag is set to true. So we'll do that later, we'll handle the firing of the weapon code, but it does mean that the energy level might not be at its maximum value. So let's do something when the fire weapon flag is set to true. Well, we know that ultimately we want to reset all of those states before we exit this routine. Let's grab the current worm that's being controlled, and we're going to get some vectors from this worm that indicate the origin of where the missile is going to be fired from and the direction, which of course is the sine and cosine of the shooting angle. And because we have a nice robust framework, all we need to do is add the missile to the object list. But I'm adding it at the location of the worm, and I'm giving it a velocity vector, which is the energy level between 0 and 1 times 40 times the direction. These values may need to be changed depending on the nature of the weapon being deployed. We'll just add the object to the list. We will need to indicate to the player how much energy they're putting into the weapon. So in the same area of the code where we're drawing the cursor to indicate the direction, I'm also going to draw a progress bar, which will be 11 pixels modulated by F energy level. So it'll be all 11 when it's 1 and no pixels at all when it's 0. And I'm just choosing the appropriate X and Y offsets to make it look pretty surrounding the worm. Let's take a look. So I'm going to deploy a unit, and currently there's no energy bar. Let's move the cursor, and I'm now going to hold down the space bar. We can see the bar filling up, and it filled up and a missile shot out in that direction. If I let go a little bit earlier, we can see the missile is given less and less energy. Let's see if we can get him to blow himself up. What goes up must come down. We saw then that when the missile flew off the screen, we lost track of it, and that's not going to be very exciting for the player. They're not going to see the consequences of their devastation. So I'm going to tell the camera to track the missile object. The downside, of course, to this is that the missile will eventually die and be removed from the list, and we don't want the camera tracking object to be pointing to an object which no longer exists. Fortunately, we capture the event when an object dies, and in this case we know that missiles explode and call the boom function. And so in this event, I'm going to set the camera to point back to the object under control. Let's take a look. Let's deploy a unit, angle the shooting angle, charge up the weapon, and release. And we can see now the missile is the focus of the camera's attention. What we see is it immediately snaps back. We don't see any of the devastation. And this could be quite off-putting for the player. One way around this is to low-pass filter the camera's position coordinates, which we've seen in many other videos, including the Retro Racing arcade game and the augmented reality in the console. The idea is that we specify a target coordinate which acts as a guide for where the actual coordinates should be, but we make it so that the actual coordinates lag behind the target coordinate. This means we no longer set the camera coordinates directly, instead we want to set the camera target coordinates. And that the camera's current position is always slowly interpolating between the current position and the target position. I've used a factor of 5 as the interpolation coefficient. Let's take a look. Let's add our unit, and if we make the unit jump around, we can see the camera has a slight lag to it. Let's fire a missile. And we see, even though we still didn't get to see the devastation, the camera panned back to the unit rather than being set to it directly. One nice side effect of controlling the camera in this way is that if the user moves the cursor towards the edges of the screen, like we've always been able to do in this setup, it can only pan a certain amount before the equations balance out. And this is nice, so it gives the player the ability to have a local field of view. However, the camera not hanging around to see the results of the explosion is still a little disappointing. We're going to need a higher level of control to decide what the game is doing at any given point, i.e. when to allow the player to actually have input, what sequence and ordering of the units are under control, where the camera is looking at any given time, updating scores and healths and checking for game win conditions. What we need is a state machine. A state machine is a set of states connected by events. And for the state machine aficionados out there, I'm going to be using a Moore machine. But the principle is, in our game engine, that we will quite happily sit in a single state until an event occurs. And when that event occurs, and depending on the nature of the event, we move to the next state. And then sit in that state until the next event occurs, etc., etc. Some events can be global, and in this case I'm going to use a reset event, which means that at any point I can get to a known state. I'm going to be using booleans to control the state transitions. And when I'm in a state, I may perform some one-time actions or set some more booleans as outputs, which can be used to control multiple other actions. Let's have a think about our game state machine. I know I'm going to want to start with a reset state, and this is where I'm going to initialize all of the game variables. I then want to go to a second state to generate the terrain. I then want to go to a third state to deploy the units, i.e. place them on the map. Once the units are deployed, the player can start playing the game. So the fourth state will be player control. Once the player has performed an action, such as firing a weapon, I'm going to go into a camera control state. The player no longer has control, and the camera is going to follow the action. And for the scope of this video, once the action has completed, we go back to the player control state. However, we've already broken our own rules of state machines. We've got to remember a state can only do one thing, and so we need a few more. For example, the generate terrain state will allocate the memory for the terrain and call the Perlin noise function. That's really one thing, and it can happen instantly for that one frame. However, the deploy unit state is a little more complicated, because my intention is to have the units parachute in from the top of the screen. So when we enter the deploy unit state, we're going to place the units at the top of the screen, but then we need a second state which represents the units in the process of being deployed. So let's get rid of that and add in units deploying. And so we sit in this state waiting for the condition to be true that the units have in fact finished deploying, and at that point we move on to player control. In the player control state, we're waiting for the player to perform a final action, for example firing the bazooka, at which point we go into the camera control state. And as we saw earlier, once the missile has hit the ground, it immediately pans back to the player that's under control. What we'd be better off doing is waiting for the consequences of the missile's actions to have finished before we resume player control. So we're going to add another state here too. To represent the state machine, I'm going to create an enumeration called GameState and have two variables, one which is GameState, which reflects the current state that's active, and one which is NextState. And this is quite important because per frame update we only ever want to execute one state. And I think the best place to put our state machine is before we handle user input, because some of the states may disable user input. I'm going to use a switch block to handle the state machine. I've added in empty case blocks to represent the different states. For now, the reset state doesn't do anything, so we set the next state variable to GSGenerateTerrain, which is the next state. But that doesn't go there straight away because this is a switch block. And that's the behaviour we want. We don't want it to execute two states during one frame update. So at the end of our onUserUpdate function, I'm going to update the current state with the next state variable. We'll initialize them to reset. Whilst I'm in the onUserCreate function, I'm going to get rid of our create map. The state is now going to handle that. We'll still allocate the memory for it, but the actual generation of the Perlin noise will now be handled during the generate terrain state. So in the generate terrain state, I'm going to call create map. That is the one action that this state does. It then sets the next state to go into the generating terrain state. For now, I'm also going to leave this blank. This state's going to do nothing. We'll see in the next video why I'm putting this state here. So this state is just going to go directly to the next one, which is allocate units. The allocate units state is going to be used for adding units to the map. So I'm just going to add one for now, which we'll put at the top of the screen. And as before, I'm going to set that to be the object under control. This state has now done its one and only purpose, which was to add units to the map. So we set the next state, which is allocating units. Now, you might be thinking, well, why do we need to have such discrete levels of states? I've just added a unit to the top of the screen. I don't want the game to continue until the unit has settled on the map. And so in the allocating unit state, I'm going to sit here and only allow it to progress to the next state once the game is stable. So I'm going to need to add a boolean which represents the stability of the physics engine. The idea here being is that when the unit is falling, we can't move on. We're still allocating the units. The unit will hit the ground and bounce around for a little bit. It's only once it becomes stable that we then go on to the next state, which is start play. This is the state that allows the player to have some control. So I'm adding a flag that represents the overall stability of the game, and we'll have to maintain this flag. Now there are probably more efficient locations to put this, but for stability, what I'm going to do is iterate through all of the objects in my list of objects and see if their stable flags are set to true. If all of the objects are stable, then I'm going to assume the game is stable. There's going to be no more movement. So all of the debris will have settled, and it's time for things to move on. In fact, I feel that this is such an important flag, I'm going to put in a little debug visualizer in the top corner. So if the game is stable, it's going to draw a little red rectangle, just to show me. We will of course remove this for the final product. I don't want the player to have any control over the object until we get to the start play state. So I'm going to create another flag which represents whether the player has control over the character. I'm going to set it to false. And for all the states where I don't want the player to have control, I'm going to make sure this flag gets set to false. So that's in reset, it's in generate terrain. I certainly don't want the player to have control whilst the terrain is generating, and nor do I want them to have control whilst we're allocating the units. And whilst the units are falling from the top of the screen, I don't want them to have control either. In fact, it's only once the player can start playing, I want to set this to true. So now I can make all of my keyboard entry input contingent on this flag. The game will remain in the start play state until the player has completed his action. So we want to have a flag for this, which I'll call player action complete, and this acts in a way as a gate, and when the player has finished an action, chances are we want to go into camera mode to at least look at the action and watch it unfurl. We know that just before we enter the play state that the player's action can't have been finished. So I'm going to set this to false here. This may indicate that actually we need another state, which is start play and playing. And I'll probably update that for the next video. When we're in camera mode, we don't want the player to have any control, so I'll set that back to false. The camera mode state is used to track the action, and so we want it to do that until all the action is finished. So we'll wait until the game is stable again, before we move to the next state, which in this case is just going to be going back round to start play again. I'll also say at this point that the player action complete variable can be reset. If you're not familiar with state machines, this approach may seem quite strange and unnecessarily time consuming, but by responding to input flags we can change what mode the game is in at any given time quite easily, and the different gameplay modes will set the flags necessary to control the simulation engine underneath. Now, as we're still early days with this whole project, we haven't got very many inputs to our state machine. In fact, right now, all we've got are the system stability flag and the player action complete flag. We mustn't forget to set this flag either, so we know that a player action is complete when they've fired the weapon. When we set up the fire weapon code, we set the camera to track the missile object that was created. and when the missile died, we set it back to the object under control. And this gave us this awkward problem that the camera immediately panned to the worm. Now we have a state machine, we've got a little bit more control over this. So I'm going to set that the camera tracking object is set back to null pointer when the object no longer exists. This makes some sort of sense. When the camera mode state is signalled to exit, I'm going to set the camera back to the object under control. So that's quite a lot of code, but let's take a look and see if it all works. So I'm starting the application and immediately we've generated the terrain and we've deployed a unit. We saw the unit fall in. I've now got control over the unit, and if I fire the weapon, the camera is automatically following the missile, lands, and we're now waiting for all of the debris to settle before the camera pans back to the unit under control. Let's just see that again. Full throttle. Big pan, lots of debris, and once it's all settled, the camera automatically scrolls back to the unit. We can also see that our little red rectangle is representing the stability state of the physics engine underneath. As the units are moving around, they're not stable. So this red flag indicates when we can move from one state to the next, if those states are dependent on stability. And so adding a state machine has made this all quite smooth and easy to build, as the state machine has allowed us to collect and use a whole bunch of Boolean flags in a far more elegant way than lots of nested if statements. In fact, we've not had to make any alterations to the underlying code to facilitate transitions from one mode of gameplay to the next. And so that's all for this video. In the next part of the series, we're going to be looking at adding more stuff to the state machine to turn this into the final game. If you've enjoyed this video, usual, give us a thumbs up. Have a think about subscribing. All of the source code is available on GitHub, and if you've any problems, leave some comments in the YouTube comments or log on to the Discord server. That's just growing in strength. And I'll just throw out a friendly reminder that occasionally I also stream on Twitch. They're not like the videos on Twitch, though it's just really just me coding and listening to cool music. But I tried one the other night and it was surprisingly more popular than I thought it would be. So until next time, take care.